Obviously, the critical factor is going to be the relation between the sea surface temperatures and convection. Is there a threshold of SST where convection gets organized? And does that mean that if the area of warm SSTs increases, then convection will also increase, or the convective integrated heating of the air column will also increase? Some things can be learned by looking at the past. So this is called CliMap. It was a reconstruction of the last glacial maximum sea surface temperature anomalies with respect to the modern times. Last glacial maximum happened around 21,000 years ago. The last ice age started to build up during the Eemian 130,000 years ago. It slowly built up, reached its maximum around 21,000 years ago, and then it started to retreat. The glaciers on the northern hemisphere, shown here for example, largely also in the southern hemisphere in these gray areas, began to retreat because of natural radiative forcing from the orbital parameters like precession, obliquity and ellipticity, and that allows us to go look at sediment cores and various other proxies to reconstruct the maximum, the sea surface temperature distributions during the height of the last glacial maximum. And you can see that large part of the oceans were colder than the present, especially the warm pool regions here in the Indo-Pacific Ocean. And we'll see a little bit later on that the threshold of convection in the atmosphere also changes when the mean temperatures change. This is still something that is not completely agreed upon, let's say, but there is evidence that at least the way we will define the temperature threshold for switching from total columnar cooling to total columnar heating will change as the temperatures change. Okay, but there are details about whether convection occurs on the warmest SST or at the sharpest gradient and so on and so forth. So there are details that we will not get so deep into. If you look at the longer time temperature anomaly going to the last glacial maximum with respect to the modern day averages, you'll see that obviously it was colder. It was in the ice age. It began to warm pretty rapidly with some hiccups called the Younger Dryas, where the fresh water of the melting glaciers presumably flooded the North Atlantic region where deep water forms, and if you put a lot of fresh water, creating deeper waters becomes harder, so the system suddenly retreated into a little bit of cooling on a very rapid time scale, which is important because rapid cooling and rapid warming are of interest when we are perturbing the climate by so much. Then we came to what we call the Holocene Period at about 10,000 years ago, where humanity began to get into settled lifestyle of agriculturalists, pastoralists, as opposed to hunter-gatherers. And the Holocene maximum here happened around 6,000 years, centered on that for a few centuries and a couple of millennia, let's say. And then we had the medieval warming, the little ice age, and then we started the industrial revolution and have started warming. And this is putting in the future scenarios of warming from various assumptions built into the scenarios under the so-called IPCC assessment, third assessment report, which came out in 2007. So I won't go into the details, but you can see that at least visually the warming rates are much faster, and one can go back in time and see that this is the fastest warming, maybe even compared to the big Paleocene, Eocene thermal maximum that occurred 55 million years ago, which is potentially was related to the release of methane that's frozen at coastal regions as hydrates and clathrates and so on. Okay, long story, but we are obviously want to understand how these temperature changes were related to tropical changes and what it may mean for the coming decades and centuries. That becomes a critical question. For that, we need to look at the relationship between sea surface temperatures and convection, or the oceanic warm pool greater than 28 degree isotherm. And looking at the relation is easier with OLR, shown here with this black solid line with the shaded area representing one standard deviation. And you can see that the OLR is low. Of course, OLR is sigma T to the fourth, so if temperature is cold, OLR is going to be small. But we know that OLR is also small where convection happens. So this is the axis is reversed, so you have to be careful. So these are relatively high numbers. Once you reach a certain threshold of 27.5 or so, there is a rapid decrease in outgoing long wave radiation, which corresponds to deep convection, clouds, cold cloud top temperatures, and lowered outgoing long wave radiation. And then there is an increase again beyond a certain threshold, and that corresponds to the sea surface temperatures with number of SST bins in a log scale, where the sea surface temperatures are warmer than the or they're in a half-degree bin in these range of SSTs. So this would indicate that the number of bins with the warmest temperatures drops suddenly as convection peaks, and then the OLR increases. This had been used to argue for a long time that maybe there is a threshold beyond which convection doesn't occur, doesn't organize. Is this really true? Turns out that not so. Again, looking at Roxy Matthew Cole's paper looking at the Indian Ocean and the South China Sea, he's looking at sea surface temperatures and precipitation, and you can see that over the Arabian Sea, sea surface temperatures do increase and precipitation increases with it, and then there is a sudden drop beyond this. Bay of Bengal again seems high precipitation over here, maybe with a little drop with warmer temperatures. South China Sea shows a sharp drop in precipitation with sea surface temperatures. But Roxy Matthew Cole argues that there is a lead-lag relation between precipitation and sea surface temperatures. So you can see that regression coefficient of SST versus precipitation, it changes sign with lead lag of a few days around this precipitation threshold that you can pick based on the region. And when he accounts for this lag, he argues that there is no such drop at the warmest sea surface temperatures. So this may be an artifact of looking for simultaneous relations between precipitation and sea surface temperatures, instead of keeping in mind that there may be a lag associated with the warmest sea surface temperatures. So just keep that in mind, that the relation between sea surface temperatures and convection is a bit complicated. This is just showing that even at intra-seasonal timescales, the relation between sea surface temperatures and convection can depend on various things, like how the ocean mixed layer depth is controlling the rate of change of sea surface temperatures. I won't go into the details, but the main point I would want to leave you with is that the SST and convection relation is a bit complicated. So we will look at the trends nonetheless. Maybe I will just include it here as this table. So you can see that percent area occupied by SSTs greater than 28 degrees centigrade, 29 and 30 degrees and so on in the Indian region and the Pacific regions between 20 south and 20 north, and 59 east to 101 east, basically the entire tropical Indian Ocean and the tropical Pacific Ocean. Various periods in the 20th century. You can see the Indian Ocean has seen an increase and the Pacific Ocean has seen an increase at for areas greater than 28 degrees C, is consistent with the figure we had already seen. Same for greater than 29 degrees centigrade, which is somewhat of a larger increase. For greater than 30 degrees centigrade, an increase, but not as dramatic as 29 degrees centigrade area. For 31 degrees, the area is quite small, but it also shows an increase. So not only is the oceanic warm pool as defined by area covered by SSTs greater than 28 degrees C has increased, but the maximum SSTs, 31 degrees centigrade, for example, SSTs greater than 31 degrees centigrade, is also increasing in area. Okay? So that's something to keep in mind. We'll come back and look at whether there is in fact some kind of a thermostat that keeps the sea surface temperatures pegged to some maximum, or can it increase as much as it wants. This is an interesting question as well, to see how the dynamic and thermodynamic responses to increased greenhouse gases or during the last glacial maximum would have affected the tropics. Okay.